seminar in our winter quarter. And today's speaker is Peter Miller, who got his PhD at the University of Arizona in 1994. And then after a large number of very postdoctoral stints, including 2 in Australia, he has joined the faculty at the University of Michigan, where he's been since, I believe, since 2000. And then so Peter has worked extensively in different problems in integrable systems, having to do with asymptotics and perturbation theory and all kind of different aspects. Today he's going to talk about universal wave breaking in the semi-classical SineGordon equation. Thank you, Peter.
Thanks, Bernard, for the introduction, the invitation. Also, thanks to Jorge for setting up all the technology. And I really appreciate everybody coming to this talk. Yeah, I want to talk about, I'm going to talk about the universal wave breaking in the sine-Gordon equation. And everything that I'm going to talk about is joint work with Bing-Ying Lu, who I think is in the audience. And she is working right now in the group of Jens Rademacher in Bremen. Okay. So I want to start out by discussing a concept, an idea, which is the idea of a universal wave pattern. So the idea is roughly that in lots of different problems with propagating waves, there's some small parameter in the problem, in the equation or something like that, associated with the wave problem. And this parameter sets some natural space and time scales in the problem. On the other hand, there are other scales in the problem because they are put in by some side conditions, like initial conditions or boundary conditions. So now you have kind of 2 scales in the problem, one that's in the, say, the equation, the other is in the initial conditions. And so there's some kind of competition, friendly competition between these 2 scales. And in some problems, the competition of these scales gets resolved with the formation of what we might call a macroscopic scale region of space-time that contains different types of microscopic oscillations, microscale oscillations. So the regions, the boundaries of these regions, as you'll see in some examples, they will depend on the scales that are in those side conditions, like the initial conditions. But if we zoom in on the boundaries of these regions using a kind of double scaling analysis, so the idea there is that this small parameter in the equation will be going to 0, and at the same time we're going to let x and t approach a boundary point of one of these domains at a certain rate. So then what we're going to see is something called a universal wave pattern that's not depending at all on the initial conditions for the problem, okay? So that's roughly the idea, but of course it's better to understand some examples. And this is the simplest example that I can think of. So this is the example of viscous shock waves in the Berger's equation. So we may think about, here's Berger's equation, and it's like a nonlinear conservation law with some diffusion, and epsilon is a positive diffusion constant, small positive number. And we set this equation with some initial data, u0 of x, that's independent of epsilon, okay? So maybe we take a bump or something like that, and we ask what happens as time increases, and epsilon should be a small number. Well, the first idea might be just to drop this perturbation term completely, and that would be the solution that we denote by u superscript 0 for epsilon equals 0. So the problem is that this u superscript 0 of xt solves this nonlinear conservation law equals 0. That's going to be, that's a problem that does not have global solutions. So in other words, the solution will develop a vertical tangent on the graph in finite time. And such a vertical tangent showing up is called a gradient catastrophe in the solution. So we'll use that term quite a bit today. But anyway, after that gradient catastrophe happens for the first time, then the sort of epsilon equals 0 solution can only be continued in a kind of weak sense. So there's a shock wave that appears at some trajectory, some moving point, x equals x of t, and there's a jump discontinuity in the solution u0 at that shock. So we may define the left and right boundary values, u plus and minus of t, by just taking the limit from the right and the left of this shock location. Then it turns out that the shock is always a downward jump. So the plus boundary value is always less than the minus boundary value. And then it's convenient to introduce the average of those two boundary values that we'll call U bar, and their difference that we'll call delta of t. That's a positive number because we've got the U minus coming in first. So anyway, that's a statement about, these are all statements about the epsilon equals 0 problem. But as soon as we put a little diffusion in, the solution of the diffusive problem, U of xt, is global for all epsilon positive. It exists for all x and t. And if we look at it, if we look at that solution for small epsilon pretty close to the shock trajectory, then what we're going to see is something that's independent of the initial data. So in other words, this limit exists. We can define a function capital U of y and t. And what y is some kind of exploration parameter. We start at the shock location for the epsilon equals 0 equation, and we add epsilon times y, and we look at that at time t. We take the limit epsilon goes to 0, and the claim is that this quantity depends only on y and t, and it's exactly given by this formula over here. So it's the average of the left and the right boundary values minus half of the difference times this hyperbolic tangent of, okay, y minus some function y naught of t that you can compute, and then divided by 4 divided by the difference of the boundary values. Okay, so this is what I would mean by a universal wave pattern. This tanh here does not depend at all on the initial conditions for the problem, and it's describing the shape of this shock wave, of this viscous shock wave. Okay, so you see all the ingredients here in the problem. There's the small scale epsilon in the problem. There's the slow scale, the macroscopic scale in the initial data. Then there's a separation of different regions when we pass to the limit epsilon to 0 happening at the shock location. And then if we zoom in on that boundary point, which is happening here, we see something that is independent of the initial data for the problem, okay? All those ingredients are there. Well, you know, another thing that you can do with the Inviscid-Burgers equation is to add some dispersion instead of diffusion. So you could add, so here again, this is the inviscid part with a numerically different coefficient that's not too important. And then plus some, okay, epsilon squared times U triple X here. So this is a dispersive correction instead of a diffusive correction. And this turns the equation into the KdV equation, the Korteweg-de Vries equation. So again, with a small parameter epsilon squared, again, with initial data independent of epsilon here. So in this situation, we're gonna see again, for small epsilon, the gradient catastrophe coming from this inviscid part of the problem here. But now, because of the dispersion instead of diffusion, the regularization is a little bit different. So we get a kind of regularization of the weak solution that's a dispersive shock wave. So anyway, it's a non-local thing. It spreads out in time, unlike the shock in the diffusive problem. But close to the moment that this dispersive shock wave forms, it has a universal character, okay? So to see this universal character, what you have to do is replace this hyperbolic tangent function that we saw last slide by something more transcendental. It's called capital U of big X, big T. And what it is it's just the unique smooth solution of this fourth order ordinary differential equation in X, in which capital T is just a parameter, okay? So for each capital T, you find the unique solution of this fourth order differential equation that obeys these given boundary conditions. So at X equals plus minus infinity, it should behave like a cube root, okay? Plus some higher order correction terms. So that determines a unique capital U of xt. And that's the thing that's important for the KdV problem. So the analog of the shape of the shock, if you like, result for KdV is this theorem of Tom Kleiss and Tamara Grava from 2009. So they say, let UC, XC, TC denote the first gradient catastrophe point of the solution of this inviscid problem. So UC is the U value, X and TC, those are the X and T coordinates of that shock formation, that gradient catastrophe. So then we let K be this number defined in terms of the initial data. It's some non-zero number by assumption here. That's for a genericity condition. And then we define scales big X and big T as basically displacements, X minus XC minus, well, this is the velocity in the frame that's moving at the scale, at the speed exactly at the shock, times T minus TC. So this is a traveling wave coordinate scaled by basically epsilon to the 6/7. And T here is a time coordinate scaled by epsilon to the 4/7. So if we hold big X and big T fixed, and we pass to the limit epsilon to 0, then the solution of the KdV Cauchy problems obeys that U of xt is equal to the UC, the critical shock value, plus epsilon to the 2/7 times capital U of xt plus a smaller term as epsilon goes to 0. So that is really the idea. We're seeing some kind of generalization of this hyperbolic tangent. It's a more complicated function, but it's playing a similar role in this dispersive problem. Okay. Now, we may discuss some kind of broader universality conjectures at this juncture. So this paper of Tom Kleiss and Tamara Grava, it was really motivated by a Dubrovn conjecture. In 2006, Dubrovn conjectured that if you take a wide variety of weakly dispersive and Hamiltonian perturbations of this Hopf equation or Inviscid-Burgers equation, or even for more general hyperbolic systems of conservation laws, the solution near a gradient catastrophe point should follow the same function, this capital U of xt. So Dubrovn said, you know, it doesn't even depend on the equation. It just doesn't matter. The only thing that matters is that you have some kind of a shock that's forming, and then you have a dispersive correction that's Hamiltonian. So his conjecture was really suggested by some formal matched asymptotic expansions, and the proof of the conjecture has only been given in the case of the KdV equation. Nonetheless, everybody thinks that the conjecture is true because there's some numerical evidence in this paper of Dubrovn Grava and Klein 2011 supporting the validity of the conjecture for other equations. So they looked at other non-integrable equations as well. It doesn't matter. They always see the same capital U of xt function. Okay. Now, what about different kinds of universality? In 2009, Dubrovn, Grava, and Klein, they formulated a similar conjecture for the focusing nonlinear Schrodinger equation that's written here. So here you have epsilon showing up in the equation in some kind of predictable places in front of derivatives like this, and also in the initial condition. So we have an amplitude A of x and then a fast phase e to the I s of x over epsilon. So this looks like a different setting somehow because, I mean, if you try to set epsilon to 0, there's no equation left over here. But if you use the modeling variables, so you introduce this kind of fluid density rho is the modulus squared of psi, and this fluid velocity u is related to psi in this way, then you can write the same problem in this form. So here you see kind of a system of equations on rho and u with some obvious epsilon squared perturbation term on the right-hand side that you might think you could drop in some situations. And the initial data for this system does not depend anymore on epsilon. So it's like more of an analog of what we've seen before. So anyway, so clearly, you know, because this is a perturbation term now, you see that it's a kind of weakly dispersive and, as it turns out, Hamiltonian perturbation of this kind of system with 0 on the right-hand side. And that's a little bit different than it was in the case of KdV because this system of equations is of elliptic type. So it's a different kind of quasi-linear system of PDEs that's showing up in the epsilon equals 0 approximation. Nonetheless, the solutions of that system can exhibit some gradient catastrophe points. And here it's a technical name, but they're called catastrophe points of elliptic umbilic type. So that's what happens for the epsilon equals 0 equation. You can run into these elliptic and umbilic catastrophe points. So, so their conjecture, anyway, the Dubrovn Grava Klein conjecture was that if you look near the gradient catastrophe point in this system, this particular system, the solution can be approximated in terms of something called the tritronquée solution of the Painlevé-I equation. So here's the Painlevé-I equation. It's a lot simpler looking than that fourth order ODE that we stared at a little while ago for a function y of tau. And the tritronquée is just the unique solution of this second order differential equation that looks like a square root, okay, as tau goes to infinity in a huge sector of the complex plane, every direction except for a wedge of opening angle, roughly 2 pi over 5, okay? So almost all directions, it looks like the square root. So anyway, this tau is a function in the theory of their conjecture anyway, it's a function of x and t that's a real differentiable map from a neighborhood in the xt plane of this catastrophe point into the complex tau plane. So you take that mapping and you compose it with this y function, and that's supposed to give you the correction to the first correction according to their theory to the wave breaking solution. So there's a problem here. There's a problem because this tritronquée function that solves this ODE in the complex tau plane, it's got infinitely many poles as it happens. Those are singularities, and the conjecture of Dubrovn Grava Klein can't possibly work near those poles. So it makes no prediction about the solution in the neighborhood of each one of those infinitely many poles. It's a good question, what happens? The first proof of this Dubrovn Grava Klein conjecture came in 2013. So Marco Bertola and Alex Tovbis proved it for a wide variety of solutions of the equation, of the focusing NLS equation. And not only did they show in their paper that, yeah, this tritronquée solution describes the first correction away from the poles, they also figured out what happens when tau is close to one of these poles of the tritronquée, and where the conjecture fails. And what they found is that near each one of those poles, the solution of NLS, psi of xt, can instead be described by what's called the Peregrine solution, or the fundamental first order rogue wave solution of the NLS equation. So here's what it is in different variables. So there's a capital psi of capital X and capital T, which is just a nice rational function solving this sort of slightly different version of the equation with a -1 in this nonlinear term. But later on, Dubrovn, Grava, Klein, and also Moro, they generalized the conjecture to general dispersive Hamiltonian perturbations of completely general elliptic quasi-linear systems. So now the scope is much bigger. We're again sort of in the situation of the original Dubrovn conjecture for the Hopf equation. We're talking about general systems of elliptic conservation laws, okay? So what I want to describe in the rest of this talk is the first rigorous results that show that a version of this generalized conjecture holds beyond the NLS special case that was shown by Bertola and Tovbis, as I indicated here. Okay. So that's kind of the background, really. And now I want to get into some of our results. And our results concern the sine-Gordon equation, like you saw in the title of the talk. So I want to describe that a little bit. So we're going to consider the Cauchy initial value problem for the sine-Gordon equation in laboratory coordinates. So here's the sine-Gordon equation. It looks kind of like the wave equation plus a nonlinear term sine of u equals 0. And we're going to formulate this with 0 initial conditions on the angle u. This u is sort of inside of the sine function, so it's natural to think of it as an angle, but with some initial condition on the velocity. So epsilon times ut at time 0 is a given function g of x. So we call these pure impulse initial conditions. So you're kind of kicking the system at time 0, but everything is stationary at time 0. Okay, so semi-classical for this problem, as you see up here in the slide title, it means that we're going to think of the epsilon as being a small positive parameter. And anyway, this equation comes up in lots of different physical applications, crystal dislocation modeling, superconducting long Josephson junctions, vibrations of DNA molecules, and quantum field theory, among other applications. But one way that you can think about what it means to make the epsilon small is to just try to get it out of this, this term over here by scaling the time. So we're going to set t equals epsilon times capital T, and think of capital T as being our new time variable. So it will be bounded, say. And then, this term over here turns into just capital U, U capital T. So two capital T derivatives of U plus sine U. Well, that's the pendulum equation over here, equals not 0, but epsilon squared times uxx, okay? And now the initial condition for this problem, because of the epsilon up here, now it disappears. So we just have that the new time derivative of u is this function g at time 0. So it's kind of a perturbed pendulum equation, and this is the perturbation term. So if you kind of ignore this, then you know that what happens in this problem depends on the energy of the pendulum that's sitting at location x, which has something to do with this initial data, which is the impulse given to that pendulum at location x. So there's an energy for the pendulum problem, and by definition, it's got a kinetic part and a potential part. And if that energy is less than 1, then you have what's called librational motion of the pendulum, in which the pendulum is just swinging back and forth, right? So that's called libration in the classical mechanics literature. But if E of x is bigger than 1, then the pendulum that's sitting at that location x is going to be doing rotational motion. So this kind of around the pivot point motion, okay? So those are kind of two different things that can happen depending really on how big is this impulse g of x that fits into this term of our problem. How big is that at a given location x? So one thing that you can do, something we did with Robbie Buckingham in 2012, was to consider what happens if you have an energy that is less than 1, say for large x out in the wings, but for smaller x, you have the energy bigger than 1. So somehow the system can't quite decide whether you should have the pendulums rotating around or swinging back and forth. So something interesting ought to happen. And what we discovered was that there's a universal wave pattern that happens near the transitional values of x, where the energy changes from being less than 1 to being bigger than 1. And that pattern appears for small time. So here's just a plot actually of some solution of the SineGordon equation. This is the x-axis and here's the t-axis. And the colors match with the angle, as you can see here in this picture over here. So anyway, so where you see lighter colors, you're near the bottom here. So the pendulums out here are just doing this librational motions or doing some oscillations around the minimum value u equals 0. But in this middle part of the picture, you see darker colors at the top, and that's because the pendulums are rotating in the middle, okay? And somehow, when you look very close to these transition points, plus or minus x critical here, the pendulums can't quite decide what they should do. And of course, that's exactly where the coupling term that you've neglected in the equation of motion on the right-hand side becomes crucially important, okay? So what happens is you have to look near this point and blow everything up and do the analysis there. And what we discovered with Robbie, just to sort of tell you one fact about it, is that there's some kinks that show up in the picture here. You can kind of see them in this picture. And these kinks are organized in the space-time according to the graphs of the rational solutions of the second Painlevé equation. So you take all the, so that turns out that second Painlevé equation has infinitely many rational solutions that can be organized by integers, the first one, the second one, and so on. And if we plot the graphs of them on top of each other, so there's the first one, turns out to be a constant, the second one has this graph, and so on. We just plot those graphs, and the claim is in the right coordinates. You have to rescale in some way. These two pictures are the same thing. This is the theoretical version. This is the version that comes just directly from this numerical computation, okay? So that's one example of a universal wave pattern that shows up in this semi-classical SineGordon equation. These graphs here have nothing to do with exactly what shape the initial data was, this function g that generates this picture. All that matters is that g prime is not 0 near this point, okay? So that's one example. But now, if we, on the other hand, consider that this impulse profile is not too powerful, so we'll assume that it's for all x, it's between -2 and 0. So then you don't get any of these transitional points at all. So the energy as a function of x is going to be less than 1 for all x in the system. So for some small times when t is of order epsilon, which is the same thing as saying capital T is of order 1, you expect that you're only going to see this kind of librational motion. So everything will be below that threshold for rotation, just doing this kind of thing. But for larger times, you know, when t starts to become big compared to epsilon, then there's some spatial variation, of course, in this energy, which will affect the frequency of vibration and so on. So you might expect that that's going to affect the picture somehow. And you might expect that you should see the generation of some periodic waves of librational type and also faster than the light speed. So of course, this is a hyperbolic problem with light speed of ±1. So there are things that travel faster than the light speed. There are things that travel slower. And these are all the faster than light type in this problem. And you may also expect to see some slow modulation of those waves as well. So this kind of picture where you have like, rapidly oscillating and slowly modulated waves is something that's described in the very first papers of Widm on his modulation theory. 1965, he considered exactly this problem. And by Widm's theory, the pendulum energy, E, and also the reciprocal phase velocity, 1 over phase velocity, which we'll call NP here, these are functions of x and t that vary on scales long compared to the typical wavelength and frequency. And those are like O epsilon in the problem. So what Widm's theory says is that these functions, E and NP, they should be subject to this, this quasi-linear system here that I've written on the slide. The J that you see everywhere is some function of E, and the primes mean derivatives with respect to E. And the E comes in this way. So this elliptic modulus M is 1/2 of 1 plus E, and the elliptic modulus ends up in these elliptic integrals of the first and second kind. So anyway, that's the system that Widm wrote down in his paper. And this system is a quasi-linear system that is of this elliptic type, just like we saw in the case of the modeling transform for the NLS equation, for the focusing NLS equation. And as I said, in the paper of Widm, he uses some modulation theory, a formal averaging procedure really, to get his hands on this system. Okay, that's where it comes from. But we might expect that we could prove that this is happening, and that's really what turns out to be true. So, okay, so it turns out that, that these elliptic quasi-linear Widm equations, they can exhibit a breaking at some elliptic umbilic gradient catastrophe points, just like the case of NLS. So in our paper, what we do is we study solutions of the SineGordon problem in the neighborhood of such a catastrophe point, okay? And as such, we're going to verify some key parts of this Dubrovn Grava Klein and Morrow conjecture from 2015. So our work is based on the integrability, the complete integrability of the SineGordon equation. So in the laboratory coordinate form, it's going to be the compatibility condition for this Fadeev-Takhtajan-Zakharov-Lax pair that you see here. So there's an X equation that's a linear equation on some vector V with the coefficients that depend on the solution U of xt and also this spectral parameter W in the complex plane. We're going to cut out the positive real line because of these square root of minus W's that you see all over the place. And then there's a similar T equation over here. Okay, so an X equation and a T equation, and they are compatible with each other precisely when the U solves the SineGordon equation in the form that we have been dealing with. Okay. So this compatibility structure allows us to solve the Cauchy problem using the inverse scattering transform. So, so the idea, just to summarize very briefly, there's a direct transform in which we put the initial conditions. So for us, that's U equals 0 and epsilon ut is this function g of x. That gets jammed into the x equation. And then we try to solve that linear equation, that ODE for V, and extract from it some scattering data. So we're going to get a reflection coefficient, which in our case is a complex valued function of positive W's. That captures the linear dependency between some certain solutions, Yost type solutions, V, that are normalized at x equals plus or minus infinity. Then there's discrete spectrum, which are values of W that are not positive real numbers. And there's what characterizes these is that there is a non-trivial vector solution V and L2. And then for each one of those points of the discrete spectrum, there's a connection coefficient, which is just a non-zero constant that captures the relationship between some normalized solutions decaying in opposite directions as x goes to infinity. And you may think of these as like reflection coefficients on the discrete spectrum, if you like. And so that's getting the scattering data. Then in step 2, one uses the T equation from that Lax pair to show that even though the time evolution of V really requires knowing the solution of SineGordon, the scattering data evolution doesn't require that. So it's got simple and explicit time evolution. And finally, this third step is to take that time-dependent scattering data that you know at a later time t and invert this direct transform from step 1 to determine the solution of SineGordon. So that's roughly the plan. Now, for us, we have the small parameter epsilon in the problem, and this appears in all three steps. Actually, the middle step, it's pretty trivial, so we'll just avoid that. But for the first and the last step, it appears in an essential way. So in the first step, that's the direct scattering transform. The job is to analyze this linear ODE with a small parameter. And because we're choosing this U function initially to be 0, the X equation is simplified actually for us. And it simplifies to this equation, which everybody probably recognizes. This is the non-self-adjoint Zakharov-Shabbat equation, where the psi that's in the initial condition here is really just -1/4 times our impulse profile G of X, okay? And the lambda is not the eigenvalue that we started with, but it's E of W, where E is this rational function of a square root of -W, okay? Anyway, the point is that epsilon appears in the problem only here. And so we see a linear ODE with a small parameter, a singularly perturbed problem that invites us to use the WKB method on it. And if we apply the WKB method with some assumptions so we're going to assume that G is a Schwartz class function, it's an even function of X, it's got a positive derivative for X positive, and it's always going to lie between -2 and 0. This last condition is to make sure that we are below the threshold for rotation everywhere for all X. So we take those assumptions and we apply the WKB method, and we get some predictions. So the first prediction is that the reflection coefficient is small when epsilon goes to 0. And not only is it small, but it's uniformly small as long as epsilon is in a certain discrete sequence of values. So we're going to not just let epsilon go to 0. We're going to let it go to 0 along a sequence epsilon sub n. And epsilon sub n is defined by this number right here, okay? It's proportional to 1/n. And if epsilon is equal to epsilon sub n, then the discrete spectrum for the problem is approximately determined by a kind of Bohr-Sommerfeld quantization rule. So we define this phase integral psi of lambda over here, capital psi of lambda, by integrating between the two roots of this quadratic polynomial in lambda here, that they're roots in the S variable. And we integrate this square root, and we get the phase integral, which is quantized in this way. So epsilon is epsilon sub n, and we want lambda k, the kth lambda value, to be to make this equation hold true, where k is an integer here. Okay, so each lambda k, it gives rise to 2 points of the discrete spectrum because we had this identity here, and when we invert to solve for w, we get 2 points from each lambda. 2 points in the complex W plane. And if epsilon is one of these quantized values, then the connection coefficients for the two pre-images of lambda k, they are both approximately -1 to the power k plus 1. So this is what comes out of the direct scattering theory by using the WKB approximation. Now, what you'd like to do is to just take the error terms in this WKB and propagate them through the inverse scattering step and figure out what happens in the Cauchy problem. But this is hard, actually. This is a difficult thing to do, to carry these error estimates through the inverse step. So I believe this is work for the future. But instead, what we're going to do is slightly move the goalposts in the problem, okay? So we're going to follow a long tradition by studying a different set of solutions than the solution of the Cauchy problem. So we're going to do the following. We're going to assume that epsilon is epsilon n going to 0, and we're going to invert the scattering transform, not on the full scattering data, which we don't actually know, but just on the leading terms, just on the WKB predictions of the scattering data, okay? So if we do that, because we don't have any reflection coefficient at the leading order, the resulting solution, which we will denote U sub n of xt, that's an exact solution of SineGordon for every epsilon n, okay? That has 0 reflection coefficient. So from the soliton theory point of view, what it really is just a pure nonlinear superposition of many solitons. And in Josephson junction problems, those solitons are called fluxons. So we call this set of solutions, this family of exact solutions of the SineGordon equation, we call it the fluxon condensate associated with the function g of x, which generated it. So G of x was our given impulse profile. From it, we get this family of functions un of xt, which are just pure capital N solitons, if you like, for the SineGordon equation. Then we study the inverse problem, okay? So we want to figure out what's happening with these UNs. And the first important thing to confirm is that you haven't really changed the problem very much by dropping these error terms in the scattering data. So indeed, you can prove that, that the UN function at time 0 is small, right? Which matches our, of course, exact Cauchy data has 0 over here. So that's not bad. And also epsilon times UN t derivative at time 0, that's our given impulse profile, G of x plus small. And this is all as n goes to infinity, and consequently epsilon tends to 0, okay? So we're recovering the initial data plus small things somehow by making this perturbation in our Cauchy data, but it's really convenient for us in terms of studying this family of solutions. So we're just going to do that going forward and rest everything on this proposition, okay? All right. So the first result that I would like to tell you is just to justify the Widm approximation. So it turns out there's an open region of the xt plane that contains the initial line t equals 0 that we call the modulated librational wave region. And I'll show you a picture in a minute, okay? So under the previous assumptions and just a little bit more that's technical that I'll leave out, we have this proposition. So we suppose that x naught t naught belongs to that that modulated librational wave region. So then there exists a neighborhood n of this point, and also well-defined differentiable functions from n to -1, 1 for the reciprocal phase velocity and also for the energy. And there is a phase defined on this same neighborhood, a real phase, such that, first of all, NP and E satisfy the elliptic Widm modulation equations that I wrote down earlier for you. Secondly, the partial derivatives of the phase function are related to the reciprocal phase velocity and the energy by these conditions here. So the x derivative is a function k of xt, which is written here, and the t derivative is a function minus omega of xt, which is written here. So these are expressed in terms of NP and E, because E is related to this M function, this elliptic modulus, in the same way that we saw earlier. So those are the first part, but I'm not finished with the proposition. The next part is that the flux on condensate obeys the following asymptotic formulas in the limit n goes to infinity. So cosine of 1/2 u is dn of 2 times phase. Here is the elliptic modulus inside of this first kind elliptic integral over pi epsilon. There's the elliptic modulus parameter. So dn function for the cosine of 1/2 u plus small. The sine of 1/2 u is minus square root of m times the Sn function plus small. And here these error terms are uniform over xt on this neighborhood of the point x naught t naught in our modulated librational wave region. So anyway, so this is really, this kind of these formulas here, these leading terms, these are like the ansatz, okay, on which Widm's theory was based. He derives the equations by assuming this, but we go a different way. We derive this directly from inverse scattering and then verify the modulation equations directly. That's sort of the approach we're taking, okay? So that kind of confirms that picture. But the boundary of this modulated librational wave region can contain one or more points where the solution of the Widm equations has a gradient catastrophe. So we're going to assume for the rest of the talk that that happens at a point by symmetry. It's going to be at x equals 0 and a time t gradient catastrophe. Okay, so since at this point the derivatives blow up while the functions themselves don't, the m value is well defined. We'll call this m gradient catastrophe. The frequency, omega gradient catastrophe, and the total phase is also well defined at that point. So then we can define sort of approximations by expanding things out through the leading terms. So c dot of t and s dot of t come from expanding the phase through the linear terms. That's all that's happening here. So constant term plus, it turns out there's no space term, and then just frequency times t minus t gradient catastrophe, same down here inside of this S function, Sn function. So those are sort of further approximations, just the leading terms really of the solution away from the catastrophe point, but we're just replacing everything by their gradient catastrophe values. Okay, so we have those things. And now I want to recall the tritronquée solution for you. So we talked about this already. So this is solving the Painlevé-I equation. It's analytic for large tau outside of this huge, small sector rather of opening angle 2 pi over 5. And the paper of Dubrovn Grava and Klein made the conjecture that this solution is not just analytic outside of this sector for large tau, but it's also analytic outside of this sector full stop. Okay, that was the conjecture. And that conjecture was more recently proved in this paper of Costin, Huang, and Tanvir. So anyway, this is kind of a picture. I'm plotting actually the real part of this Hamiltonian associated to the y function in the complex tau plane. So the 0 levels are these red curves. So you see outside of each one of these poles, there's a little loop that kind of sinks into the pole as we move further out in the picture. And everything, all these poles are contained exactly inside of this sector of opening angle 2 pi over 5. That's the Costin-Huang-Tanvir result. And the green dots are the locations of the poles by this Fornberg and Widm and numerical method. Okay. So now, so I can now tell you our result, our main result here. So the first correction term near the gradient catastrophe point. So we have this gradient catastrophe point 0 times GC. So then there's a positive number sigma that depends on our initial data. And there are related constants, capital M and little a, okay, which are written here, and a related constant B, positive, okay? Such that the fluxon condensate UN of xt that's associated with this impulse profile G obeys the following asymptotic formula. So cosine of 1/2 of UN of xt is the C dot function. That was like the leading term leading term of this problem away of this function rather away from the catastrophe point, approximated in the phase by linear terms. So that's what that is, plus an epsilon to the 1/5 correction that has this Cn function in it, and also a kappa of xt epsilon, plus small terms, ordered epsilon to the 2/5, and a similar looking formula for the sine of 1/2 UN function. So the thing I want to draw your attention to is this kappa, this amplitude. It's some real quantity, which is exactly the real part of the Hamiltonian of this tritronquée function evaluated on a linear argument in x and t, okay, scaled by epsilon to the power 4/5. And this approximation is accurate as long as as long as x and t are close to the catastrophe point by size epsilon to the 4/5. That's what this says here, okay? And also as long as we are not close to a pole of the tritronquée, which is the same as saying that y is bounded, okay? So we're picking up an amplitude that's related to this tritronquée solution, to the real part of its Hamiltonian. And then there's some things that look like the leading terms that we saw before. So maybe I can just mention a few facts about that. So the leading terms S dot and C dot and S dot, those are independent of x and t, of x rather, periodic in t, and there's an exact x independent solution ut of the SineGordon equation, which because it's independent of x is really the simple pendulum ODE, such that C dot is cos of 1/2 u and S dot is sine of 1/2 u. These formulas that I just showed you, they're consistent with the Pythagorean identity, of course, through the terms of order epsilon to the 2/5. Since the Hamiltonian is a short symmetrical function, the formula that we're getting are consistent with cosine and sine being even functions of x, which is an exact fact for the problem. And finally, this amplitude kappa, it's slowly varying compared to the leading terms, okay? And if we interpret it as a constant, the correction terms satisfy the linearized SineGordon equation. And here we are linearizing around this pendulum formula, u of t, okay? Also, this kappa vanishes along certain curves because it's the real part of the Hamiltonian that vanishes on the red curves that we saw in the picture back here, these little red curves, okay? So, all right, so this is just a picture. So this kind of green region here, that's the modulated librational wave region for the problem, I'm showing you solutions for different values of n. So this is n equals 8 on the left, n equals 16 on the right for some impulse profile. G of x is minus hyperbolic secant of x. And the blue dot is the theoretical gradient catastrophe point location, okay? And so what I just want to say that what we're seeing here is some kind of different pattern that's showing up inside of this part that's not the librational wave region. And we're going to try to explain what's happening there just close to this catastrophe point. That's the idea. So, so the first thing is just to draw the pictures again and isolate some region that's of the correct size. So that should be of size epsilon to the 4/5. Actually, that was the scale that we said we should look on to see this tritronquée. So that's what's happening. We just isolate these boxes of size epsilon to the 4/5 that are based at this same gradient catastrophe point. And now I'm going to just blow up those boxes, okay? I'm going to blow them up. So that's the blowups of these boxes now are here and here. Okay, so this is the scale of this tritronquée, and consequently I may plot on these pictures the images in the xt plane of the poles, which are the green dots coming from the Widm encode. Okay, so those are the same green dots in both pictures. The rest of the picture is still changing a little bit because epsilon is changing. Okay, so that's the idea. The conjecture is that sort of in this scale, away from these green dots, these two pictures are both going to have a modulation described by this same tritronquée function on this exact scale of these pictures here, okay? And the shrinking, these kind of defects that you see in the picture, they're kind of getting a little bit smaller as we make epsilon smaller. And the theorem that I just showed you asserts that these have to shrink into the green dots actually as epsilon goes to 0. They have to disappear into the green dots. So now what are these defects? So to describe those, let's let m be some elliptic modulus and omega be a phase parameter. And we're going to describe some family of exact solutions, u of xt m omega, okay? Solving the SineGordon equation in this form. So, so here's just some notation. So first of all, xn will be our shorthand for the three elliptic functions, Cn, Sn, Dn, evaluated at an argument like this. And then P is a similar thing, except that it's a periodic and not elliptic function that's gotten by just integrating basically minus 1 over dn squared, take away its average, okay? So we integrate that, and that's going to give us a periodic but not elliptic function, P of W. Okay. And now, so the C dot and the S dot functions that we had before can be written in our notation now exactly as just the dn and minus square root of m times Sn. So that's the leading terms. And now I'm going to define a rotation matrix, an orthogonal rotation matrix. So it's got diagonal elements that are written in terms of a function R and a function Q by this formula, and off diagonal elements are written by this formula. And the Q and the R are written here in terms of the elliptic pieces and also this periodic but non-elliptic function P. There's also a rational dependence here, or I guess polynomial dependence on X and T that will become rational in the P in the matrix R. Okay. So now the solution that I'm talking about can be specified in this way. So cosine and sine of a half of big U is rotation matrix acting on that wave that's coming from the sort of leading terms, C dot, S dot. And since the Q is of order T and the R behaves like this as X and T grow, then you can show that this R function tends to the identity matrix at infinity. So it's really a localized perturbation of this background wave, okay? So it's a space-time localized perturbation of an exact elliptic function solution of SineGordon that we may regard as being a rogue wave on a periodic background. Okay, so here's just some pictures of it. So, so when m is very small, whenever m is very small, the background wave is also very small, but nonetheless, there's some localized perturbation. You can kind of see it in the cosine plots here and the sine plots down here. It's space-time localized, but it's very hard to see because m is very small. But if you make m a little bit bigger, so here I think m is a half, for m being a half, now there's some kind of obvious space-time localization in both the cosine and the sine plots. And what's happening going left to right is just you're changing this phase parameter omega. The cosine plots here and here at the end, this is 0 and pi for omega. They are exactly the same. The sine plots change the sign. Okay. And then here's an extreme case. So this is where we're very close to m equals 1, which means that the background wave train is basically a train of separated solitons or kinks. Okay. And now we're seeing that there's a very strongly localized structure that's appearing here in the problem. So those are exact solutions. And then the theorem that relates to those, it says the following. So let tau p be a pole of the tritronquée. So then we define coordinates capital X and capital T that are basically 1 over epsilon times x minus xp and t minus tp. Xp and tp, that's just the image in the xt plane of that pole tp. Okay, so then cosine of a half un and sine of a half un can be written exactly as cosine and sine of a half capital U, where that is our special solution, plus order epsilon to the 1/5 correction terms. Okay, so this is an accurate approximation when the big X and the big T, which are the coordinates of those rogue waves, are held bounded. Okay, that's the result. So to illustrate the result, we go back to these same pictures that you've seen already. These are in the plane where we're seeing the modulation by the tritronquée, and we isolate another box here centered at the first pole. And this box looks the same in these pictures, but it's not really. It's of size epsilon to the 1/5, which is almost the same, but not quite when we have the value of epsilon here. But that's the scale really on which we're supposed to see the rogue wave. Okay, so we're going to zoom in now and make those boxes the same size. So that's this picture. Okay, so here's again n equals 8. N equals 16. The claim is that these are converging to the same thing. Okay, that's the claim. And we can really pick out the values of the parameters for which we should plot the solution, the exact solution, to make a comparison with these pictures. And that's what I can show you over here. So these are the exact solutions for some, again, we don't capture the phase value in these plots because we're showing the whole sequence of them. But it's one of these pictures should be compared with what we saw back here. And I think that's fairly good, fairly convincing agreement. Okay, so I'm just going to show you one slide about the proof and then we'll finish. And if there are questions, we can talk in more detail. But we start our formulation by setting up a matrix Riemann-Hilbert problem whose solution characterizes this fluxon condensate that's associated with the given impulse profile G. So we start with a Riemann-Hilbert problem, and then we apply the Dave-Joe steepest descent method, and it's in its numerous elements. So one of the elements that we have to adapt to the situation is this so-called G function that appears in the theory quite a bit. And what we have to do to make it work in this case is we have to allow for some more severe singularities in the G function at 2 distinguished points in the spectral plane and use that singular G function to prove the existence of some conformal mappings near these 2 points. So that's a thing that has to be done. And then the steepest descent method leads us to a global parametrics, an approximate solution of the Riemann-Hilbert problem that consists of an outer parametrics that captures this kind of elliptic oscillating background near the catastrophe point. And the second part are local parametrices near these same 2 points where the G function has to be modified. And near each one of those are somehow going to unfold the wave breaking. Those parametrices are solved in terms of the Painlevé-I tritronquée function, okay? Well, not quite. We have to worry about the fact that there are poles in the problem. Whoops, there are poles in the problem. So, okay. So near these tritronquée poles, unfortunately, these local parametrices just don't exist at all. And so we have to fix them up in the following way. So we make a gauge transformation of the unknown in the problem. That solves the jump conditions exactly, but it leads to a worse match with the outer parametrics on a disk boundary. And consequently, that has to be fixed. The way you fix that up is by introducing a suitable Becklin transformation of the background periodic wave. And that's the thing that produces at the end these defects that we see in the pictures. Okay, so that's the summary of how to do it. So the conclusion is that for a wide variety of initial conditions, the semi-classical SineGordon equation exhibits universal asymptotic behavior near a gradient catastrophe point in its Widm approximation. And the first correction term to that Widm approximation near the catastrophe point, it involves really the real part of the Hamiltonian for the tritronquée solution y of tau for the Painlevé-I equation. So this correction term is consistent with these broader universality conjectures like the Dubrovn Grava Klein conjecture. And it's also valid near the catastrophe point, except near points that get mapped to the poles of this tritronquée function y. And near each image in the xt plane of one of those poles, we may regard that sort of domain as kind of a defect in the background periodic wave. And that defect is going to be modeled quite accurately by a special periodic solution, particular solution of the SineGordon equation that is, what it is, it's like a rogue wave on the periodic background. It's space-time localized perturbation of an elliptic function. Okay, so that's my talk. I'll finish there and take any questions about what I've discussed. Thanks for your attention.